Hi everyone. Till now we have seen what predicates are, how they are quantified and how they are compounded. In this lecture we will see how they are negated. We saw in the previous sections how De Morgan law was represented for sets and propositions. We also saw for two propositions P and Q, the negation of P implies Q is equivalent to P and negation of Q. To derive and understand De Morgan's law for predicates, we first need to understand how we negate quantified statements. There are two rules for negating quantifiers given by the theorem of generalized De Morgan's law for logic. The first law states that the negation of for all x p of x is equal to there exists x such that negation of p of x. This means that when the negation is expanded, it reverses the quantifier and negates the inner predicate. For the second expression, negation of there exists x such that p of x is equal to for all x negation of p of x. Again, we can see how the negation is reversed the quantifier and negated the inner predicate. To understand it better, let us see the proof for the same. If we want to prove that this statement is true, we must prove that both the constituent statements have the same truth values. For that, let's make a small truth table. If negation of the expression for all x p of x is true, then we can say for all x p of x is false. This also means that p of x is false for at least one value of x. Negating both the sides of the equation, we can say negation of p of x is true for at least one value of x. Or mathematically, there exists x such that the negation of p of x is true. In case where negation for all x p of x is false, then negating both sides would mean for all x p of x is true. This means that there cannot exist any value of x for which p of x is false, or in other words, there exists x such that negation of p of x is not true. Mathematically, it can be represented as the following. Now we see the truth values match, thus proving the rule. Let us consider the second one. For the equation negation of there exists x such that p of x is equal to for all values of x negation of p of x. Again, to prove this statement, we will map the truth values for both of the constituent statement. Let's start with the LHS. If negation of there exists x such that p of x is true, then there exists x such that p of x is false. This means p of x is false for every x, and if we negate that, we can say that for all x negation of p of x is true. In case it is false, we can say that it is its inverse. There exists x such that p of x is true. This means it is not true that p of x is false for any x, or mathematically, for all x negation of p of x is false. Now again we see the same truth values, and thus the De Morgan's law for logic is proved. This takes us to identify the general rules for negating quantified predicates with respect to the concept of the domain of discourse. Let us consider a domain of discourse A which contains the value for a free variable x. For such a constraint, we can represent the De Morgan's law for logic as the following. Negation of for all x belongs to the domain A, p of x is equivalent to there exists x in the domain A such that negation of p of x is true. This is the same formula we saw earlier, just that the variable x is restricted to the domain A. The negation reverses the existential quantifier to universal and negates the predicate, although the quantifier and the variable belong to the domain. It gets interesting when we try to include multiple domains, and that is where the principle of compound predicate comes into the picture. For example, for two domains A and B, and the predicate Q of x, y, where the variable x belongs to the domain A and the variable y belongs to the domain B, we can say that the negation of the predicate for all x belonging to domain A, there exists a value of y in domain B such that Q of x, y. This is equal to there exists x in the domain A for all values of y in domain B such that the negation of Q of x, y. We can also express the counter statement, the negation of the predicate. There exists x in domain A and for all values of y in domain B, Q of x, y. It's same as for all values of x in domain A and there exists a value of y in domain B for which negation of Q of x, y is true. From both the statements, it is evident that the negation reverses the quantifiers and applies a negation to the predicate, the same as we saw before. Let us discuss the compound proposition AND. Consider n different propositions P1, P2, P3 up to Pn. Let's compound this and then it becomes P1 and P2 and P3 up to Pn. So basically the conjunction of all propositions. We can say that the second statement is true only when all the values of P1, P2 till Pn are true. This is an example of universally quantified proposition and can be represented as for all x, P of x. This is a general expression for statement 2. If instead of AND it is OR, again considering n propositions P1 to Pn, applying the OR would give us the disjunction of all the propositions P1 or P2 or up to Pn. Let this be statement number 4. We can say that statement 4 is true when at least one of the values among P1, P2 up to Pn is true. This is called the existentially quantified expression and can be represented as there exists x such that P of x. This statement is said to generalize the statement 4. So now that we know how compounded propositions are expressed in terms of predicates, we can finally conclude De Morgan's law for predicate logic. From De Morgan's law of logic, we have the following expression. The negation of the conjunction of P1, P2 through Pn is equivalent to the disjunction of individual negations of P1, P2 through Pn. Let this be statement number 5. From the generalized De Morgan's law, we have the expression negation of all values of x in such that P of x is equivalent to there exists an x such that negation of P of x. Let this be statement number 6. We can say that statement 6 is the generalized De Morgan's law expressing the meaning of statement 5. Notice the resemblance in the structure of both the notations. We can see the same for the second expression. We can call this as statement number 7. This is a negation of disjunction of all the propositions, which results in the conjunction of individual negations. The generalized De Morgan's law for the negation of the existentially quantified predicate can be represented as the following. Negation of there exists x such that P of x is equivalent to for all values of x in negation of P of x. This can be represented as statement number 8. Similar to what we saw for the previous expression, in this case, statement 8 generalizes statement 7 and is thus called the generalized De Morgan's law. So with that, we're done with all the theory behind predicate logic. As we saw, predicate logic is extensively used to understand English statements and convert them into mathematical notations which basically the computer can understand. We form a larger algorithm based on these predicates and their premises. There are several types of English statements, so to understand it all, it is advised to practice a lot